Thank you very much for your invitation. Can you hear me?
Yeah, we can, yeah.
Yes. Yes. This is joint work with, this talk is based on joint work with Carl Kuhlman and David Sherry. And it was based on an article just published in London Mathematical Society newsletter, and other articles published in journals such as the British Journal for the History of Mathematics or Kentness, and etc., as you see on the list. So what I would like to discuss is similarities between the procedures of Leibnizian and Robinsonian calculus, and also address some objections by historians. I will speak about something perhaps unusual, trichotomy, not the dichotomy, but the trichotomy of ordinals, cardinals, and originals. And of course, I will explain what I mean by originals. And the point that we're trying to make is that comparison with non-standard analysis facilitates our appreciation of some of Leibnizian procedures that may otherwise seem obscure. The point that we make is that Leibniz used genuine infinitesimals and genuine infinite quantities, which he thought of, of course, as useful fictions. Useful fictions, unlike some of his contemporaries, which believed in their in their real existence. Unlike some other Leibniz historians, we hold that they're not merely stenography for Archimedean exhaustion. I will get back to that point in the course of the lecture. And what we argue is that Leibniz procedures find better proxies in non-standard analysis than in modern Weierstrassian mathematics. We mostly follow the interpretation of Leibniz in a seminal study by Boss from now 50 years ago. So here is a table that illustrates some of the dictionary between some of the Leibnizian terms and the terms in non-standard analysis. The Leibnizian relation of infinite proximity, his law of continuity, his distinction between assignable and inassignable numbers. A particular Latin term that he uses in his work called infinitum terminatum. We will see what that means. He mentions Leibniz in some of his work that infinitesimals, he makes it clear that infinitesimals violate Euclid's Book 5 definition 4, which is essentially the Archimedean property, closely related to the Archimedean property. Also, Leibniz uses terminology of constant differential. We see what that means and how that's, what kind of analogs we have for that in non-standard analysis. So the 6 items that we saw on the table, let's try to go over them. The first one is, what kind of equality is Leibniz dealing with? Leibniz emphasized that he worked not with the relation of exact equality between quantities, but rather equality up to negligible infinitesimal terms. And here's a quotation from Leibniz where he says that. I think that not only those things are equal whose difference is absolutely zero, but also those whose difference is incomparably small. And although this difference need not be absolutely called nothing, neither is it a quantity comparable to those whose difference it is. In other words, it's infinitely small compared to the quantities which it is the difference. And this, of course, can be described as a relation of infinite proximity. And in non-standard analysis, of course, we have a related procedure which involves taking the standard part of a limited quantity. Let me remind you that a limited quantity is a quantity that's smaller in absolute value than some standard number. Sometimes it's called finite, but it's not always appropriate to use the term finite for this term limited. Item number 2, law of continuity. There are several formulations that one finds in Leibniz of his law of continuity. Also, law of continuity is not exactly the same as the principle of continuity. In any case, one of the formulations of Leibniz's law of continuity is the statement that the rules of the finite are found to succeed in the infinite. And vice versa, says Leibniz. This is very interesting. There's an if and only if kind of condition, which, as Robinson already pointed out, is remarkably close to our, in other words, Robinson's transfer of statements from R to R star, to the hyperreals, and in the opposite direction. Here at the bottom, you have You have the French original of the statement by Leibniz. Item number 3, assignable versus inassignable. Leibniz mentions frequently a distinction between assignable and inassignable quantities. As when he writes, for example, here dx means the element, that is the element in the modern sense of sort of element, a infinitesimal element of length or volume. That is the instantaneous increment or decrement of the continually increasing quantity x. This, by the way, was translated by Boss. Notice that parenthetical terms are also added by Boss. It is also called difference, namely the difference between two proximate x's which differ by an element or by an inassignable. That's the term I want to emphasize here in Leibniz. He refers to dx as inassignable. Differ by an element, the one originating from the other, as the other increases or decreases momentaneously, says Boss. The parallel distinction in non-standard analysis between standard and non-standard, not only numbers, but it applies also to all sets. And distinction is used routinely in the procedures of modern infinitesimal analysis. For example, as I mentioned already before, an infinitesimal is a number smaller in absolute value than each standard positive real. Similarly, a definition of continuity of a function of f at the standard point x is given in terms of infinitesimals, as Cauchy defined it already in 200, almost more than 200 years ago, that an infinitesimal change in the variable always produces an infinitesimal change in the function. Item number 4, what is bounded infinity? Leibniz has a treatise, a lengthy treatise called De Quadratura Arithmetica that he actually never succeeded in publishing. This dates from 1676. In proposition 11, more precisely in the scholium following the proposition 11, Leibniz uses a type of line segment that he referred to as infinitum terminatum. Now, what is infinitum terminatum? Literally translated, this means bounded infinity. Now, such an infinitive number is supposed to be greater than any assignable line segment, and it is contrasted with unbounded infinity. Unbounded infinity, which Leibniz sometimes refers to also as infinite whole. According to Leibniz, those are contradictory and useless. You cannot use them in mathematics. But bounded infinity you can use in mathematics, and in fact he does. You use them effectively in calculus and geometry. So in any case, what could the expression bounded infinity possibly mean? Incidentally, Robinson, in his chapter on the history of mathematics, in his book Non-Standard Analysis, in chapter 10, he makes no mention of the use of such an expression. It's not clear if he was aware of it. In the Weierstrass paradigm, the term bounded infinity may sound like a contradiction in terms. Cantor and Weierstrass, of course, are behind the great accomplishment of creating rigorous foundations for analysis. On the other hand, they also conditioned mathematicians and historians both to hold that there are just two types of infinite number, ordinal and cardinal. Only two types of infinite number. What we would like to say is that it's for understanding Leibniz, it's better to work with a trichotomy of ordinal, cardinal, and original. It is helpful to get beyond the ordinal cardinal dichotomy and allow also for the possibility of what we call original. What is a original? A original is an element of an ordered number system, a ring or a semi-ring. That's why it's called a original, that is greater than all naive integers. And as an example, we have a non-standard integer in the semi-ring of hyperintegers, hypernatural numbers extending the natural numbers. That would be called a original in our terminology. And infinite terminata is analogous to a segment of unlimited length, greater than all segments of standard length. Therefore, infinite terminata, which played a crucial role in the Leibnizian calculus by enabling non-Archimedean phenomena, they could be thought of as understood in modern terminology as original. That's what the bounded infinity is. It's original. Item number 5, infinitesimals themselves. In his letter to his ally Varignon, Leibniz described an infinitesimal as an infinitely small fraction, or one whose denominator is an infinite number. 1 over infinity, in other words. Here at the bottom, you have the French original for those who are interested. Leibniz has a seminal paper from 1684 where he described all the rules for developing the calculus, including what's called the Leibniz rule for the product. Now, the question is, how does Leibniz define an infinitesimal? The Leibniz has an article. A lot of Leibniz's work was not published, but this particular article is published, and in 1695, it contains a rebuttal of a criticism by I don't know how to pronounce this, Neuventit, who was also worked in infinitesimal analysis and produced a book of his own, and he criticized Leibniz's approach. I'm not going to get into the details of this particular debate, but this article is interesting for us because Leibniz made it clear that his incomparable quantities, when compared to one, they violate the comparability notion formulated in Euclid. Book 5, definition 5, as Leibniz says, and in modern editions it appears as definition 4. So here's Euclid's definition. Any magnitude may be multiplied as many times as to exceed any given homogeneous magnitude. And of course, we recognize the Archimedean property here. Notice that it's stated here as a definition, not as an axiom. So Euclid already envisioned the possibility that this definition may not necessarily be satisfied. Leibniz made similar comments about the violation of the Archimedean property in the letter to his ally L'Hôpital. And in Nassar analysis, of course, infinitesimals violate the Archimedean property, just as in Leibniz. Item number 6 from our table, which is a final item. Leibniz historians mention the use of terms such as progression of variables and constant differential. Boss, for example, writes, Leibniz explains that if dx is taken constant differential, that is, one may treat the quadrature as integral of y without writing dy, as is done in the theory of indivisibles. But if one wishes to consider different progression of the variables, the quadrature has to be evaluated as integral of y dx. Such comments can be formalized in modern infinitesimal analysis in terms of a uniform partition of a standard segment into infinitesimal subsegments. For example, one computes an integral via an infinite Riemann sum corresponding to such a uniform partition. Now, non-constant differentials, as opposed to constant differential, would correspond to a partition that's not necessarily uniform. Again, an infinite partition, but not necessarily uniform. Those are used sometimes also. The idea of a progression of variables that Leibniz speaks of, and Leibniz historians speak of, may seem odd to a modern reader accustomed to think of a variable as ranging through a continuous range, but is completely natural from a viewpoint of infinitesimal partitions in Nassar analysis. They're used all the time, for example, the definition of a lobe measure. Finding proxies in Weierstrass framework, which of course would be possible, would be more difficult and necessarily involve an infinite process rather than a single partition, because such a framework does not have infinitesimals. Now, what do historians think of all this? In the context of a discussion of the Leibnizian calculus, a historian expressed the following reservation about our approach. The view that Nassar analysis is pervasive in the history of math is a legitimate, though wrong in my view, thesis that anyone has a right to defend. Good. So it's good to know this legitimate. Now, what's wrong with it exactly? Now, one thing I have to mention right away, that Leibniz planted 2 seeds. Leibniz planted 2 seeds for the development of analysis. Both the Archimedean seed, when he spoke of exhaustion, Archimedean arguments in the style of what's called Archimedean exhaustion arguments, and also an infinitesimal seed, so to speak, the A track and the B track, as we refer to it in some of our publications. And he also stated remarkably that those are equivalent. He insisted in many papers that these are equivalent. Of course, he has no logical tools to prove that sort of thing. But Leibniz definitely planted 2 seeds. Now, getting back to the comment by this historian, there are at least three possible ways of interpreting the wrong claim. What would be the intended target of such a reservation, of such a criticism? Number one, As you know, non-standard analysis, the way Robinson presented, uses ultrafilters. So one could jump perhaps to the conclusion that Leibniz is also dealing with decimals. So maybe Leibniz used ultrafilters. Okay. Number two, perhaps he's referring to the claim that Leibniz's procedures find better proxies in non-standard analysis than modern Warshausian mathematics. Or the claim that Leibniz's decimals were non-Archimedean and not merely stenography for Archimedean exhaustion. So let's examine those one by one. Three possibilities, perhaps you have other possibilities you can mention. In any case, claim one would clearly be an anachronism. Nothing further needs to be said. With regard to claim two, it's certainly reasonable to maintain that Leibniz was neither a Weierstrassian nor a Robinsonian, while both can be helpful in understanding aspects of his work. But that's not the claim here. The claim is that one can analyze the procedure of Leibnizian calculus to gauge which modern theory provides better proxies for his inferential moves, and which modern approach helps us better to understand his calculus. For example, Leibniz historian Knobloch, which is a well-known Leibniz historian, he emphasized the importance of the infinitum terminatum in his early articles. And as we mentioned, the analog for this is only available in an infinitesimal framework, such as a ringinal in non-standard analysis. With regard to the last claim, final claim, number three, certainly Leibniz was no mere stenographer. More to the point, one can ask the following. This is sort of the elaboration of claim three. When Leibniz used the term infinitesimal, did he just mean to reader to fill in the details of the corresponding Archimedean exhaustion argument, as in Ishiguro's synchytogrammatic interpretation from 1990? This interpretation reads the passages containing the term infinitesimal as shorthand for Archimedean exhaustion. In other words, in the philosophical parlance, the term infinitesimal does not refer. Leibniz scholarship today is an area of lively debate, and I will say more about this later. Let me just say a couple of words about other infinitesimalists. Cauchy often uses genuine infinitesimals, as for example in his definition of continuity. But he had less interest in philosophy than Leibniz did, and he produced work mainly without looking for underlying philosophical principles, with the possible exception of his Torino lectures that he gave in the 1830s. While there are a few mentions of assignable quantities in Cauchy, there's definitely no mention of, not that I found, of inassignables, or for that matter, of infinite determinata or anything like that. Leibniz viewed principles such as his law of continuity as philosophical insights. Today, we view its counterpart, the transfer principle, as a mathematical insight. The point here I'm trying to make here is that Cauchy was less interested in philosophy than Leibniz, and therefore did not get as far as Leibniz, foundationally speaking, even though he was, of course, much ahead of Leibniz, mathematically speaking. And a quick comment about Fermat. Fermat developed a method named inequality. We wrote a couple of papers about this. This is not the place to get into details. One thing I do want to mention is that Fermat was extremely cautious, and we have very little indication of what he thought about his increments, E, that he used in his method. And indeed, there were good sociological and theological reasons for his caution. Some of the opposition to this kind of mathematics stemmed from a perceived conflict between indivisibilism and transubstantiation, as codified in the Council of Trent in the previous century, in the 16th century, Session 13, Canon 2. However, this I can elaborate. This is not the place to get into the details. We have argued that Fermat's inequality is indeed best understood as some kind of relation of infinite proximity. One important point that I would like to emphasize is the distinction. The viability of interpreting Leibniz in terms of NSA depends crucially on the following distinction: procedures versus foundations. What does this mean? The analogy that we developed, in particular those listed in the dictionary, concern the role of procedures. As far as the foundations are concerned, as we said, Leibniz rejected infinite sets and infinite wholes. Almost all of modern mathematics is formulated in terms of Cantorian set theory. So there's definitely no Leibnizian basis for that. But it may be pertinent to mention the existence of at least two distinct approaches to null-set analysis. Robinson's original approach, as developed in the 60s, involved extending the field of real numbers to the field of hyperreals. A decade later, Hrbacek and Nelson independently developed axiomatic approaches to null-set analysis. I gave a talk last year about this. I'm not going to get into all the details, but one important point is that in such axiomatic approaches, infinitesimals are found not in an extension, R star, but rather in R itself. And similarly, non-standard integers are found in N itself. Yes, somebody had a comment? What enables this such approaches is introduction of one-place predicate standard, postulating the existence of two types of real numbers, not just numbers, but also other entities, other sets, standard and non-standard. While traditional set theory works, as we all know, in the epsilon language, where epsilon is the membership relation, the underlying set theory of axiomatic approaches to non-set analysis works in the stepsilon language, or ST epsilon language. In axiomatic approaches, infinitesimal is a number small and absolute value of every possible standard real number. Hrbacek and Nelson showed the conservativity of their theories over the traditional Zermelo-Fraenkel set theory with choice. As I mentioned last year in my talk, you can do away with choice now. This means that the introduction of a new predicate does not involve any new foundational commitments. It does not, in principle, prove any new theorems, although it has develops a more powerful language. Now, as I mentioned, our claim to parallels between Leibniz and Robinson, yes? Between Leibniz and Robinson, concern.
It's okay, Mikhail, continue. Someone had the mic open, so I closed it.
Oh, okay. Concerns the procedures. We talk about analogs in procedures of the Leibnizian calculus and Robinsoниan calculus. Nonetheless, I would like to make the following point about foundations also. One could ask the question, which foundational approach to non-set analysis is closer to the spirit of the Leibnizian calculus? And one would have probably to answer that the axiomatic approach, as developed by Hrbacek, Nelson, and also others later, is closer, since the existence of inassignable infinitesimal is postulated by Leibniz, as we postulate in non-standard approaches, in axiomatic approaches, we postulate the standardness predicate, rather than resulting from any kind of extension construction, as in model theoretic approaches, such as Robinson's original approach. So here we list some of our papers in the British Journal of History of Math, in Journal for General Philosophy of Science, in Review of Symbolic Logic on Leibniz, in Erkenntnis, in Revista Latinoamericana de Filosofía, and the Studia Leibniziana, the professional Leibniz journal. And here we have a couple of Leibniz, seminal Leibniz papers that I mentioned in my talk. Here are the seminal papers in the field: Hrbacek's paper, Nelson's paper, Robinson's paper, and Skolnick's paper from a couple of decades before Leibniz, before Robinson. I would like to mention also the paper by Ogagli and myself on the evolution of Leibniz's thought in the matter of fictions and infinitesimals. How much time? Do I have another couple of minutes?
Literally 1 minute.
1 minute. Okay, good. I think I'll be able to finish. So I would like to ask the following question. Is our work controversial with the historians? So consider the following 4 items. Item number 1. Obviously, we have the opinion of the editors of the reviews of these professional history, philosophy, and logic journals who thought that our paper, our research in Leibniz is valuable. So that's the first item that I'd like to mention. Item number 2 that I'd like to mention, I'd like you to check out the following title by Arthur and Rabois on the unviability of interpreting Leibniz infinitesimals through non-standard analysis. Emphasis, of course, added. Emphasis added is not emphasis not part of their title. Item number 3, on the failure of the correspondences alleged between non-standard analysis and Leibniz's conception of infinitesimals. And finally, item 4, which is Exhibit A, check out this conclusion of a referee report we received from Historia Mathematica, editors-in-chief Anthony Mallet and Jeffrey Oakes. So hold on to your seats. I was about to call the manuscript a slapdash collection of bits and pieces randomly strung together, but that would be too generous. The authors have not even attempted to string their scatterbrained thoughts together. They have merely placed a bunch of random scraps adjacent to each other and submitted the resulting monstrosity as a research article. And therefore, our conclusion is that, yes, our work is controversial with some historians. This final section is meant as an introduction to Mina Peterson's talk on logics of malicious and abnormal behavior in social networks. And as a final remark, a postscript, the previous slide was supposed to be the final one, but then last Friday we heard from the editor of Professional Logic Journal that our latest article has been accepted for publication. Thank you for your attention.